we will be using to define a band. And then the similar V lower and V upper for the next time instance data. So these two parameters are for the lower and upper limits of the current instance data, and then the same data for the next time instance. We'll copy them and just paste it. And so this is one array of the counter array which will count the transition. These are the two numbers, band row and band column, which you can see in this sheet. If you can see the cursor, we are in uh, 3 comma 2, third row here. The cursor is cursor's position. So the row number is 3 and column number is 2. So that number will be identified with these uh, two parameters. So we make 5 bands here, and we take data points equal to 800. So out of 935 data points, we are going to use here only 800 data points of the filtered drive cycle, or filtered drive cycle that we recorded, not the generated drive cycle. We dimensionalize this V data array. Mm, So this counter is 2D array of 5 rows, 5 columns. So at first we will load that velocity data for each case. So whatever is your seat number s- or seat name, you can write here. So here I have saved all these data in this seat EM501. So I am writing here EM501. If you have saved in the seat 1, then just write seat 1 or any other name which you might have assigned to this seat. With writing this next, we end this for loop. Okay, so for loop will be executed in this region only. And what for this for loop is it is loading data in this v data array. Where from it is extracting this data, taking this data that is in this seat EM501. EM501, which row, which column? So it is shown here. You can see 6 plus int k. So when int k is equal to 1, so that will the first entry in this v data array, and that first entry, so int k is equal to 1 at that time, 6 plus 1, that is 7th row, second column. And so you may see here how these data are stored. They are stored, they have some offset here, a row offset. So we have row offset of 6. So from 1 to 6, data are not useful to us. So our useful data starts from 7. So the same offset we have added here. So that is 6 plus int k and column second. So this loop will load all this data, velocity data in this v data array. And now what we have to do in this first stage, after loading this data, we have to monitor this data uh, for every instant of time for its. Okay, sorry for this break. Uh, so once this data is stored in this array, what we will do, we will monitor this data for its entire time length uh, to find its velocity band or the class as we named it. So what we will do again, we will use this for loop, and that for loop will be spanning for this entire length of n. N means here data underscore points. So here we are using this nested for loop inside the loop. So one for loop for this entire length of the data, and then we have one another for loop, and length of this for loop, or total number of iterations in this for loops, is equal to total number of bands. Okay, so what we will do, we will select for a particular time instant data, then we will check that to which band this data belongs. Then so for that we need one for loop. This is the inner for loop. So that is just to identify the uh, class or the state or the band of that particular instant of time. So what will it will first, it will select the band 0, first band, which has the velocity from 0 to 10, and when q is equal to 1. So when q is equal to 1, the lower velocity is 0, upper velocity is 10. Sorry, lower velocity is 1 and upper velocity is 10. So this is the band, first band, or the first class, uh, the first row. You may see here this one, the first one, who's, and now it will check uh, that whether the time instant velocity picked here for this int p, uh, it falls in this band. So we will use if statement. Okay, so what it is going to do, it will select any time instance data, and then we will use this for loop. And for this, inside this for loop, it has some for particular value of this q, uh, there is some minimum velocity and there is some maximum velocity corresponding to that int q, or corresponding to that band, we can say the band. So if our velocity, selected velocity data at int p, if if it falls in this range, then what will happen? It will tell that this band rho is equal to int q, means that data belongs to this particular row. So if velocity is 27, please tell me if there is any problem to understand this logic or this language here. If you have any problem, please ask, or we can continue otherwise. Okay. Um, am I audible, sir?
Yes, sir. Yes, sir. You're audible.
Okay. Okay. So okay, we move forward. Okay then.
Yeah, I think no questions.
Yeah. Yeah. Okay. They don't have any doubt, so we may move forward. And same now, what we will do. So this loop will return this band row as a number for that current velocity data, or the current velocity, current the velocity at current for the current instant. And now the same thing we will apply for the next movement. So here we are going to enter the column number. So what this column number will tell us? Just select any row. Okay. Suppose we have selected this. Suppose we have selected this. Our data is in second row at any instant of time. So it means the velocity at that particular time is uh, between this 3 kmph. Now what we have to do? We have to find out that what is the velocity at next time instant. So, so sorry. Uh, we have to row number is fixed from this loop which we just wrote here. Now we have to find the column number. And why column number? So if the vehicle's velocity in the next time instance also remains in the same band, then column number is uh, sorry, here the second column. So the column number will be defined by the velocity of the next time instant. and whereas this row number is defined by the velocity at of the current instant. Okay. So same thing we will repeat here. Just we will use these data with this. So instead of V lower, we are using this V next. So so whenever such thing happens means such thing happens means suppose what we have to do, how we have to fill this matrix. We will be filling this matrix first using this number of transitions. So suppose vehicle's velocity was at 5% at 5 seconds suppose, and at 6 second its velocity becomes 30, becomes 25. So what has happened here, that at that particular moment there was one transition. So for that what we have to do, that 20 to 30, what was the transition? 20 to 30. So here this so whenever this transition happens, this type of transitions, we have to increase the entry here by number one. And how we will ensure that thing, or how we will implement that thing, uh, using these two loops. Okay, so if the velocity data is, and then we will put one counter here. Okay, so whenever this type of transitions occurs, what we will do, we have this 2 by 2 counter matrix, and in this counter matrix, whenever this transition occurs, we will increase the entry. Entry means the entry belongs to the previous entry plus one, and for this entry, this band row and band column, how they are obtained? They are obtained using these two loops. Okay, so this counter is our TPM matrix in terms of number of occurrences, not the exact, not the probability. And then what we will do, we will divide this number of occurrences in a row to the total number of occurrences, and then it will give the probability. And now we have to extract this matrix, or we have to print this counter data in a particular sheet. So once this is filled, we will print it. And here we will end this P loop. Sir, 1 minute, it hanged.
Okay, sir.
So next in P means this for loop is closed. So from here to here, the data is in one for loop. And now we are going to print this matrix at our desired location, uh, this counter matrix. So obviously this is 4 by 4 matrix, sorry, 5 by 5 matrix. Int I is equal to 1 to number of bands. Size of the matrix is band cross band, bands cross bands, and then 4 is equal to, this data we take out in this EM50. We give offset of 2 for both row and column, 2 plus int I. So this code is over now. So what it will generate? It will generate this TPM in terms of number of occurrences, and then we will convert that TPM uh, in terms of probabilities. So we will run this code and we'll see that what happens with this data. So where is this data? Data is here, velocity data, and this plot, the data is plotted here in this graph, this blue color graph. You may see this data. So it will use this first 800 data of this series, and then it will make this TPM here. So where will be the TPM? TPM will be TPM is here. So once we run this code, it will result like this. So just 1 minute. So just click on this run sub button, and it will generate like this. You can make it 0, and we'll run this code, and it shows like this. So what these entries mean, we'll copy and paste these entries here. So there were 447 occurrences when the velocity, what was the band here? This was band 0 to 10, 10 to 20. So the vehicle's velocity was from 0 to 10, and it remained in the next instant also in 0 to 10 uh, uh, value, or in 0 to 10 range for 447 occurrences. Okay. And so total number of this occurrences were 800. So for 800 data, uh, the velocity was in this first band at 10 instant, and in the next instant also it remained in the first band, and then for 8 uh, instant of time, the velocity was in this for 9 occurrences, the velocity was in 0 to 10 speed range, and in the next instant of time, this velocity is speed up, and it sends jump from this band to this band. So these are the total number of occurrences. Or and what we will do, we will sum the entries of all these rows. and then we will divide all these entries divided by this number. So row entry here, this is equal to, we have to fix it. So now these entries are in terms of probabilities. So 0.98 means 98% probability is that vehicle, if vehicle is in state 1, in the next instant of time also it will be in state 1, and the remaining probability, or there is a 0.019%, 0.19% chances that it will change its state. And why it happens, the why values are very small, because we have selected this we band's length is as 0 to 10. If we make more number of bands, these probabilities will be, we will see the higher values of these probabilities. So this is how this TPM is generated, and we have taken one very simple example. You may increase this number of bands, and you may also insert more number of variables in this while creating this TPM. This is just velocity based TPM. You can make uh, velocity, and both velocity and acceleration based TPM also. So what is the acceleration at any instant of time, and what is the acceleration at for the next instant of time. And or similarly we can make this TPM based on the states. States means, as we discussed yesterday, we can make uh, so many states with this data states. So here you can see blocks, different blocks are there. So each block represents one state. So, and this is in acceleration and velocity plane. So instead of going just using only single velocity data, we can use both acceleration and speed data to define a state, and then we can make this state transition matrix. So here in this example that we solved today in this VBA code, here state was defined just by the velocity. So this state may have so many variables as it's shown in this picture. Uh, so we can use so many parameters, and we can make the TPM accordingly. Now, what we will do after using this with using this TPM, so once this TPM is generated, okay, so this is one TPM where so many total number of bands are 9 here, and you can see these velocity, sorry, these probability entries, they goes on decreasing as we move from left to right. And now, what we have to do with this probability matrix? So we already have snippets. So many snippets we have made, uh, as we discussed yesterday. And now, Okay, okay, so we have to join all these snippets again to make one drive cycle, and snippets are the segments of this drive cycle, and we can, if we join them, then we will get a drive cycle again. So how we have to join then is the snippets? We will be using this TPM, and then other than along with this TPM, we have to use this Marco chain process. So in the MATLAB, and in this Marco chain process, what we will do, we will generate one random number S. So that random number S will be generated, and based on that value of that random number S, we will be joining these snippets together. And what is this Marco chain theory? This Marco chain theory is simply states that the the value at next instant of time, it depends only on the value at the present state. So we will use that this Marco chain process in conjunction with this Monte Carlo simulation, and where we will be generating this random number S. And if the value of this S is such that here you can see this Pij is these entries. So suppose if I say P11 is this first entry 0.2. So now you can find out P uh, how it is going to increase with increment in K. So here what it is going to find out, it is going to find out this cumulative probability. Cumulative means we are adding these probabilities along this length. So that is the sigma here, j is equal to 0 to j is equal to k minus 1. Okay, so we will add these probabilities together, and then we'll make one another matrix. Okay, and in that matrix, we have these probabilities entries, and that is called cumulative probability and matrix. And what we will do, the first entry will be 0.57, second entry will be instead of this 0.2626, the second entry will be this is 0.2626 plus the previous entry. Then the third entry will be the sum of these three. Fourth entry will be the sum of all these four. So that is called cumulative transition matrix. And so here this Pij, this summation, it gives actually this cumulative probability only. So we will generate this random number here, and if the value of this random number is such that uh, this this cumulative probability at any instant is lesser than the cumulative probability entry of the next state. So if this value is smaller than cumulative probability at any state is smaller than this, uh, so S, just 1 minute, sir. So you may see this, if this condition meets at the, so that value of S we will be selecting, and that value of S will be representing this that value of K. Okay. So if we know the value of K means that particular uh, module or the particular class that which belongs to this K number, or the particular snippet which belongs to this K number, that will be our next snippet to be added with the present snippet. So using this theory, we will be adding all these snippets. So we have one snippet, and then what we have to do, we have to add one more snippet to it. What we will do, what we have TPM. we will generate one random number, and then we will check this condition. If this condition meet, what we then what we will get our next instance or the next snippet, which is to be connected um, with this current snippet. So that value will be the k value. So snippet belonging to this k value, that will be the next snippet. So we continue by we continue this iteration till we end up this complete length of the drive cycle. So this is how this drive cycle is made. And then, so here uh, we took one this two-wheeler data, and you may see it was a two-wheeler Activa, Honda Activa, and this is the raw data for the Monday, and similarly we took raw data for 14 continuous days, and this is for Friday, and this is synopsis of uh, the data of obtained here. Uh, what is the maximum acceleration, what is the maximum speed, and all these things. And then we did filtering, and these are the snippets again. And then here you can see that total number of snippets generated to generate a, so total number of 150. This is class 1 where the average, so we have four classes, we used four classes, and 1 2 3 based upon their average speed. So from 0 to 45, 50 was the maximum speed we selected, and total number of seconds you can see here, and total number of snippets you may see here, and what was the average velocity, what is the duration. So the number of snippets are around here 500 600 snippets were generated, and then using this technique we made four different drive cycles, CD1 to CD5. So these are the performance parameters or target parameters of these five candidate drive cycles that we generated. And so this is drive cycle 1. You may see here CD1, and for this drive cycle 1 it is shown here it's mm, spectrum, acceleration spectrum, what is the occurrence of a, so what we found that maximum time this acceleration is uh, less than 1.5, uh, and the, the acceleration which is whose probability is very high, and this was 0.5 meter per second square. So all these data, so similarly this was the drive cycle number 2. Then this is candidate drive cycle number 3, CD4, and this is CD5. So we made total 5 drive cycle data, and now what we will do after this drive cycle data, uh, which is the next part here. Uh, Before we start this next segment, uh, please tell me if you have any doubt up to this point. Okay, if you don't have any doubt, then we may continue. Uh, so now this is one
Okay,
seat.
sir.
Okay, sir.
Please continue.
Okay, sir. This is one seat where we are going to use this drive cycle data, and from the drive cycle data, we are going to find out this vehicle's power rating, the motor's power rating, and as you might have seen in today's session, that these are the two characteristics we need. Okay, the first one belongs to the peak power, and the second one for the rated power, and here this red dot, it shows the rated uh, base power at rated. It corresponds to this rated power. Okay, so this is the torque and this is the speed. Okay, so now what we will do with this drive cycle data? So here the first column is the drive cycle data in kilometer per hour, and second data is the first data we have converted into this MKS, and we have the velocity in meter per second here, and then as we did yesterday, from this velocity in meter per second we calculated this acceleration, and then FW in this column N. Here you can this is the windage force on this vehicle. You might be knowing this all these expressions. So that is windage force. Similarly, the entry in the column O, this is the force required to accelerate the vehicle. F is equal to ma. So we have the acceleration value, we have the vehicle parameters. So vehicle parameters are here: 200 kilometer vehicle, buoyant is required, gravitational G is 9.81, AT, which highly deviates with the region or geography, and then aerodynamic drag coefficient, which totally depends upon the vehicle body type or overall structure of the vehicle, or uh, then frontal area of the vehicle, and road angle. So road angle for this study we have set. You can change this road angle from 0 to any value, and the values are written here in degree. But in calculation, this Excel uses the radian values. So you may convert while applying this value. Radius of the wheel, and then okay. What we did here, we have the velocity. So we can, from the velocity we can find out all the, if we know, if we have the velocity profile, we can find out all the forces exerted on the vehicle. How? Because this windage force is a function of velocity, v square, acceleration F is equal to ma mdv by dt, friction coefficient, which mostly is constant, but also it depends on the velocity. So all these forces are added here, and this is the net force acting on the vehicle. And then the speed of the vehicle, we have this speed in meter per second, and we have to find out this speed in radian per second. So v is equal to r omega. So omega is equal to v velocity divided by radius, wheel's radius, and radius is given here. So the speed of vehicle in radian per second, and this is the speed of the wheel. So till now we are the data the, we are working with the data at wheel. So this is the wheel's speed and this is the wheel torque. So torque is equal to force into force cross this radius uh, or the, and then power. Here the power is P is equal to T omega. So torque is calculated here, and omega is known to us, which we found from this wheel's radius and the speed of the vehicle. So using all these force datas we calculated from the velocity data. So from this force data, we uh, moved from this translatory motion to this rotating motion. So we found this wheel torque, and then the wheels omega radian per second. And then what we are going to do, so here this term is there, gear ratio. Okay, so now we are moving from wheel to motor. Okay, so if we move from wheel to motor, if there is any gear, so cumulative means the overall effective gear ratio means the multiplication of all gear ratios, intermediary gear ratios is there. So here we have taken one. Obviously, it is more than one, because differential itself it gives the gear ratio of 4 to 7. So, but this is since here we designed a hub motor for the scooter, so their gear ratio was one only. Uh, and then this is the motor RPM. After multiplying this gear ratio, we get this motor RPM, and then motor torque, which is the torque at wheel divided by this torque at sorry divided by gear ratio. So and then we divide everything to the efficiency of this gearbox. So you can see this first and second row in column AB and AC. So two gear ratios, these efficiencies are given. So if we divide these the torque required here to this multiplication of these two gear ratios, we will get this the effective torque, shaft torque required at the motor's end. And so finally, the data here in this Z column, this is the motor torque. So what we have the velocity. So suppose we have some velocity here in this column 14. So at that time our velocity is around 9, which is 6 kmph, 6 kilometer per hour, and corresponding to that 6 kilometer per hour, we have the motor torque is equal to 38 Newton meter. Okay, and what is given, and given that the acceleration is 1.2, so acceleration is very high. That's why the torque requirement is very high, because at this very small speed, windage force is very small, and friction is almost constant for this low speed. And so we need this much amount of torque. So sorry, okay, I'm sorry. The data is 51. So torque requirement for this 6 kmph, corresponding to this 6 kmph with the gear ratio 1, and for the defined motors or vehicles configurations, we need this much amount of torque. And then what we will do, we will plot this graph RPM. So x-axis will be the motor RPM and the y-axis will be the effective torque. And if we draw this data, we get this type of plot. So you can see here all these dots uh, belongs to this velocity instants. Okay. So these are the different torques corresponding to these different time instants. Total number of dots is equal to total number of time in seconds. So for every second we have one dot. For every second we have one velocity of the vehicle and we have the torque corresponding to that velocity. Okay, so this is what we get from the drive cycle. We get the velocity profile and then we use this vehicle's specifications, and from the uh, velocity profile we find out the torque requirement for that drive cycle for every instant. And now we have the torque data, and then we have to define our motor's rating. So here you may see we have two graphs here. One is shown in yellow, one is shown in silver. So this yellow color graph, it shows okay, let me uh, okay, okay, just 1 minute. Okay, so here we don't have any graph now, and you can see here in the column AB, column AB and AC, that base speed, maximum speed, and then constant power. So base speed means the rated speed for which the motor is going to run. We selected base speed as if we select base speed as 300. So we make these two characteristics here, and what is there in these characteristics? We have to find out. We have to use just this if statement, that if the torque requirement is less than this rated torque, and or the speed is less than this rated speed, then torque is the rated torque, or else uh, the torque is equal to power divided by omega. So this if condition we have applied here, and because we all know that the torque is constant up to the rated speed. Okay, if we design a motor for the constant torque region, so torque is constant up to this rated torque, and power is obviously going to increase. And then what happens? Power remains constant, and torque starts to decrease. So power P is equal to T omega, that is equal to constant, and then torque is equal to uh, power divided by omega. And which power that is that? That is the this maximum power where power becomes constant, and which is called the rated power. And so what do we have to make this characteristics? So till the RPM is less than base RPM, we will have the constant torque value, and that constant torque value is equal to P rated divided by omega rated. And after that, if the velocity is greater than this rated velocity, at that time the torque is equal to uh, P rated divided by omega. Okay, so this is logic we have applied while getting this data, and this data uh, we pasted here, and if we paste this data here, we get this thing here. Now you can see here, if we increase this constant power, which is in column 8, then what will happen? Obviously, torque will increase. This would have been increased. Now, what if I increase this base speed? What will happen if we instead of using this base speed 300, we use base speed 500? You can see that motors operating range uh, may increase, but at the same time, most of the time the vehicle is overloaded because torque requirement is reduced. So we have to select this. Now, suppose if we make the torque rate base speed 200, or let's make it 50, 100. So, so the same motor means the motor's power rating is same, 1200 kilowatt, 1200 watt motor. If it is designed for designed with base speed of 100 RPM, uh, we can't fit this motor to this vehicle. Why? You may see here that most of the these operating points, they are far below this motor's characteristics. So motor will be highly under underloaded in terms of torque, and so we have to uh, find one this optimized value of this base speed, such that motors does not remain overloaded for most of the times, for most of the data points. So here we selected 300, and similarly the second the silver color characteristics, it belongs to the peak power, and the peak power we found from here that how much peak overloading we over how much we can overload this vehicle. So this range is 2.75, and base speed peak speed for this overloading, that is 270, and this peak power for the overloading is 2100. So for that power 2100 we found, for that power 2100, and the base speed of 270, uh, we calculated this data similar to the calculation of this data, and this data again we pasted here. So this is the motor's characteristics, required characteristics for the peak power uh, or maximum power, and this one is for the rated power. So, so this is how we have to use this drive cycle data for this motor. So please tell me if you have any doubt up to this point. Okay, sir. If they have any, don't have any doubt,
Yes.
then
Yeah.
I think we have completed from my side up to.
Okay.
So
Okay. Yeah. Yes. Dear participants, if you have anything to clarify, sir is with us. So you can ask if you have any queries. I think no one is having any, I think,
Oh,
doubts.
oh,
So I think.
yeah. Okay, sir. Okay.
Uh, Sir, I want to know like this data that you are using, is it collected from the pit or is it just a random some data?
No, 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 sir.
This
Actually, we ran this vehicle.
okay,
I show
okay.
you. Uh, so using this Activa. Uh,
Yeah. So I wanted to know how to collect this data actually.
okay, okay, sir. 1 minute. So I have. Sir, this is one GPS tool. This app is there,
Okay.
the Android app. So we can use this app, the
Okay.
GPS Speed Graph Plus. Okay, and whenever we want to collect this data, we can activate
Hmm.
this app, and then it will automatically collect all these velocity data. Uh, I show you how.
Okay. So this is a device which is we cannot do it from the mobile phone, right? So we need to,
Yes,
I
no,
think,
no, no. We can do
have this
from the
device.
mobile, not any device, sir. This
Okay.
mobile app.
Okay.
Yeah, yeah. So this,
So mobile having GPS can the
hmm,
yeah.
hmm.
Mm.
So this type of data it generates. We can later on we can connect to our desktop PC, and then we can
Mhm.
take all these data. So here you may see that date and time, latitude, longitude, altitude, everything is there. Speed,
Mm.
maximum speed, or like that. So total distance. So everything with it can
Great,
fetch
great.
from this GPS. It will be made available by this app.
Okay. So, sir, for a particular vehicle, how do you collect on a daily basis or like how
Okay.
there is a particular means in a hourly basis or on the basis of the work because there has to be particular
Yes, sir. Actually,
condition, I think.
we ran this vehicle for 2 weeks. So for every day, we were collecting data for three segment of the
Mm.
of a day. Morning data at 8 a.m. So at 8 a.m. We used to go
Mhm.
for a 20-kilometer run inside this Guwahati
Mhm.
city, through this Guwahati city,
Okay.
and then afternoon also, then evening also. So
Yes.
like that, we rode this vehicle for 14 days, and then this GPS data we collected.
Wow, great, great. That is very interesting. I think that can be done for different location, I think, because different location will
Yeah,
have
yes, yes,
different
yeah. The different
sets
location
of
also,
data.
yeah, it can be done, sir. Because you may
Yes.
see the seat
Mm.
which I have shown here. In this seat,
Mhm.
what is missing is this. You may see the grade road angle in this
Mhm.
19th entry. So this
Yes.
road angle is zero. Okay, so we can make this road angle
Okay.
5 degree, 6 degree, but it is not always
Mhm.
possible that this road angle is constant throughout this
Mhm.
run. It goes on changing. So
Okay.
we can make one column here, and in that column we can
Yes.
put this longitude, sorry, this altitude data. So from that
Okay.
altitude
Okay.
data, differential altitude data, uh,
Okay.
uh, we can we can
Okay.
find
The same
we
data
can
can
add
be
this another term.
extracted from the
Mhm.
GPS. Yep. Mhm.
That thing is not implemented here because the route was completely flat only. Only these flyovers were there. If we move from
Okay. Got it.
move along this
Mm.
Guwahati, so there is not
Yes.
that much change in this altitude inside the city.
Okay. Okay. Yeah. So
So
even we sometimes have to go down also. So in that case,
mm,
we need a negative kind of elevation. Yeah.
yeah, negative. And if we want to go to this that Kamakya temple or this type of
Yes.
vehicle is designed specifically for that purpose only. So at that time,
Mhm.
this information is required. We can't leave
Yes.
this column unadded, this value unadded.
Yes. Yes, sir. I find it very interesting. I don't know about the participants. I don't know why participants are so quiet. I think you have explained it very clearly, sir. Actually, each and every steps were very slowly and very smoothly explaining. So I think so things are very much clarified. So
Okay.
I thank to you, sir.
Thank you, sir.
Thank you very
Okay,
much.
sir. Thank you, sir. Thank you
Yeah.
to invite me.
Yes. So participants, you have any questions? Last, let me just ask if anyone is having any. I think that's all. I think so,
Okay,
sir.
okay,
Thank you
okay, sir.
very much for joining and
Okay, sir.
sharing the.
Thank you to you also,
Yeah,
sir,
yeah. So,
to provide me this
yes.
opportunity.
Thank
And yeah, I will be thankful to all of
thank
to
you.
you and
Thank
thankful
you
to
very
this
much, sir.
our audience. Yeah, who could bear with me. And thanks to all. Thanks to all.
Mhm. Yes, sir. So yeah, hoping to see you in the future also, sir.
Sure,
Thank you so much.
sure. Ji,
Thank you,
sir.
sir.
Thank you.
Okay, sir. Thank you. So, dear participants, thank you very much for joining. This is the end of today's session and today's last session, in fact. And we are hoping to join again tomorrow in the morning. So, at 10 a.m., we'll be having again our Dr. Rajesh Kumar Panda from Power Grid, and he will be discussing on a few things on the EV charger and EV in the Indian market. He's looking after the smart grid department of Power Grid. So we'll get to know the implementation part and all those things regarding the EV charger and all. So see you tomorrow again in the morning. So thank you very much and see you tomorrow.